Recall last time we discussed backtracking. We define it as a systematic exhaustive search technique or searching technique, and this would produce the optimal solution at a longer time. Now this first description here and the second are considered advantages. So the advantages of backtracking is number one, this one here, the first, it is systematic and it is exhaustive search technique. And second advantage is that it will produce optimal or the best solution. Just like what we did before when we traverse the whole tic-tac-toe game sub-tree, we visit all the descendant nodes from the root node to all the leaves. So that is exhaustive because we visit all the tree nodes from the root node down to all the descendant nodes. We traverse the whole tree. So that is an exhaustive search technique. And since we have visited all the nodes, we are certain that the solution we got is the best one. There is no other better solution because we have searched all the nodes. We are certain that we will get the best solution because we have searched the whole tree. We visited all of the nodes. The third one, which is this, is considered a disadvantage. Okay, so the third one falls here. This is the first, the second description, and the third description falls here in the disadvantage. The disadvantage of backtracking is that it will take a long time to produce the optimal or to find the optimal or the best solution. The reason why it takes long time because we visit the whole game tree, meaning we visit all of the tree nodes. Now, there is another search technique we call alpha beta pruning, which uses backtracking technique, but it will prune or skip some nodes. And this process, the alpha beta pruning, involves the notion of final and tentative values for nodes, which we have already discussed last time when we perform backtracking, depth first search traversal on the game tree tic-tac-toe, so that we assign evaluation values to all the nodes starting from the leaves up to the interior nodes and finally up to the root. Okay, remember the discussion we have with the game tree tic-tac-toe, how we set or assign evaluation values to all the nodes starting from the leaves, going up to the interior nodes, and finally going up to the root node. And once we get an evaluation value for the root node, then we could answer those questions we have in mind as to, number one, who would probably win at that point of the game, and number two, what should be the best legal move that the player at that point in the game will take so that the likelihood of him winning the game will be maximized. So the advantage of alpha beta pruning, which uses backtracking technique, is that it will allow the pruning or the skipping of some nodes. So if we're going to compare now the standard backtracking or the normal backtracking versus the alpha beta pruning, the disadvantage of backtracking, which is it takes a long time to produce the optimal or best solution, this is solved in alpha beta pruning. So this is longer time to produce the best solution. while in here, shorter time to produce the best or optimal solution. So for backtracking, it has number one, description, which is it is a systematic, exhaustive searching technique. Second, description is that it produces optimal solution. And the third, which is considered a disadvantage, is it takes long time to produce the optimal or the best solution. While for alpha beta pruning, since this is still backtracking with a twist, or this is like backtracking search technique, it will allow the skipping or the pruning of some nodes, so that because some nodes are skipped or pruned, they are not visited. And so since you don't visit some nodes, the process would be significantly shortened. So alpha beta pruning, since this is still backtracking, it would still be considered a systematic search technique, but it's less exhaustive. Okay, so it is less exhaustive because it allows the pruning or the skipping of some nodes. Second description is the same. It still produces the optimal or the best solution, just like backtracking, the normal or the standard backtracking. So for description number one and number two, backtracking and alpha beta pruning are the same, except that for number one, for backtracking, this is exhaustive search technique, while for alpha beta pruning, this is less exhaustive, and therefore it shortens the process of finding the best solution. While for the normal or standard backtracking, it is exhaustive. It visits all of the nodes. It does not skip or prune some nodes. It visits all the nodes. Therefore, the process is longer. But still, it will produce the optimal solution. We have here that three rules for computing the final and tentative values for the nodes. Now, we already demonstrated number one and number two when we assign tentative values and final values to the tic-tac-toe game 3 in our previous video. So that is already applied, the rule number 1 and rule number 2 for backtracking. The normal backtracking involves only these two rules, number 1 and number 2. Remember that we applied these two rules when we perform backtracking in our previous tic-tac-toe game 3. Okay, we applied rule number 1 and rule number 2 in assigning evaluation values from the leaves up to the interior nodes and finally up to the root. Number 3 is applicable only for alpha beta pruning. So for normal or the regular backtracking, only rule number 1 and rule number 2 are applied. But for alpha beta pruning, these three rules are applied. Okay, so for alpha beta pruning, it applies rule 1, 2, and 3. So again, backtracking applies rule number 1 and 2 only, while alpha beta pruning applies rule number 1, 2, and 3. So again, when we do alpha beta pruning on a tree, we are just actually doing backtracking technique, search technique, but this time we are also going to allow the pruning or the skipping of some nodes. And for alpha beta pruning, we are going to apply all of these three rules. While for backtracking process, we only do rule 1 and 2. So this is for backtracking, rule 1 and 2. For alpha beta pruning, it's rule 1, 2, and 3. So say for example, we have this tree where this is the root of the tree, and all of this here on this level are the leaves of the tree. And these ones here on this level are the interior nodes. Now remember, when we discuss backtracking, when we assign evaluation values to the nodes, you start with the leaves. The assigning of evaluation values starts here in the leaves. So say for example, these leaves have this evaluation values 7, 3, 8 respectively for all of these leaves, and that the interior nodes do not have evaluation values yet, and also the root node has no evaluation value yet. So this is the rule that allows us to prune some nodes, rule number 3. So this is not applied in backtracking, therefore backtracking will visit all of the nodes and it will not skip or prune some of the nodes. So this time, let's try to apply the ordinary backtracking search technique. So on this level, the nodes are min nodes. On this level, the nodes are max nodes. On this level, the nodes are min nodes. And so when we do backtracking, starting from the root node, okay, doing depth first search traversal, okay, this is where we start, and then we go here. This has no value yet. We go here, visit this node. This has no value yet. And we visit the leaf. This has a value. So we propagate this evaluation value 7 of this leaf node, this child node, to the parent node. So this has a tentative value of 7. This parent node has a tentative value of 7. It is tentative because there are still 2 children nodes to visit, which is this leaf with evaluation value 3 and this leaf with evaluation value 8. And then we go down by depth first search traversal. We visit the second child. Then we propagate its evaluation value, which is 3, to the parent node. And we update by rule number 2, we update the tentative value of this parent node by getting the mean or the minimum of 7, the tentative, which is coming from the first child, and also the evaluation value of the second child. So you get the mean because this node is a min node on this level. You get the minimum value between 7 and 3. So the minimum is 3. So we change the tentative value of this parent node to 3. This time, the tentative value of this node is 3. And then we go down, visit this node, and we propagate its evaluation value, which is 8, to the parent node, and then update the tentative value of this node by getting, again, the minimum between 3 and 8. So the minimum of 3 and 8 is 3. So this is still the value, the evaluation value of this parent node. Now, since there are no more children node to visit, we go up by rule number 1, which says that if all the children of a node n have been considered or visited, okay, when all the children nodes are visited or pruned, meaning there are no more children nodes to visit, make the tentative value of that parent node final. So when you go up, leaving this node, the tentative value 3 will become final. So let's write it here. The 3, since it's already a final evaluation value for this node, when we go up, we propagate this final evaluation value of this child node of this parent node up and set that value 3 as the tentative value for this node, the parent node of this child node. And then we go down, this has no value yet, and then we visit this leaf, we propagate its value 5 as the tentative value of this node. And then we go down to this leaf with evaluation value 1, and then we update the value of this node by getting the mean. Since this is a mean node, getting the minimum between 5 and 1. The mean is 1, therefore, the new tentative value now of this node is 1. We go down to this node, and when we go back to the parent node, we propagate this final evaluation value, which is 9 for this child node, to the parent node, and once again we get the minimum of the tentative value of this parent node and the final value of the third child. The minimum is 1, okay, so it's still 1. When we go up, leaving this node, we make this tentative value 1 final. So 1 is the final evaluation value for this node. And then when we go up back to this node, the parent node of this node, we update the tentative value of this node by getting the max. Since this node is on this level, max nodes, this is a max node, therefore we get the maximum between 3 and 1, and the maximum is 3. Okay, and when we go up, we have no more child for this one to visit. We make the tentative value of this node 3 to final. So this becomes a final value 3. When we go up back to the root node, we propagate this final value of this node to this root node, which is the parent node of this node, with a final value 3. So the tentative value now of this root node is 3. And we go down to this subtree and propagate 6 to this parent node. So the tentative evaluation value of this parent node is 6. And then we go down to 2, and then we update the tentative value of this node by getting the minimum of 6 and 2. And that minimum value is, of course, 2. So we change the tentative value of this node to 2. And then we go down to visit the leaf with a final evaluation value 4. When we go up to visit this node again, we update the value of this node by getting the mean, because this is a mean node, getting the mean between 2 and 4. The mean is 2. Okay, and then when we go up, that tentative value becomes final. So we make it a final value. So this has a final value of 2. And then when we go up back to this node, we bring this evaluation value to propagate it to the parent node. So this parent node of this node will have a tentative value of 2. And then when we go down, visit 7, set this as the tentative value of this node. Then we go down to 5, update the tentative value by getting the minimum of 7 and 5. And the minimum, of course, is 5. So we change the tentative value of this node to 5. Then we go down to visit 8 and go back to this parent node. Get again the minimum of 5 and 8. The minimum is still 5. And since we go up, leaving this node, there are no more child node to visit for this parent node. We make this tentative evaluation value 5 final. So this node has a final value of 5. And when we go up, we update the tentative value of this parent node by getting the maximum of 2, the tentative, and 5, the recently visited child node, with a final value of 5. So what is the maximum between 2 and 5? It is 5. So we change this tentative value from 2, now it becomes 5. Then we go down to this child node and to this leaf, propagate 1 as the tentative value of this node. After that, we visit this leaf with evaluation 2. And when we get back here after visiting this leaf with evaluation value 2, we get the minimum of the tentative value of this node and the final value of the recently visited child node. And the minimum is still 1. Okay? And we go down to visit the third and the last child node. Once again, we update the tentative value of this parent node by getting the minimum of 1 and 9. And the minimum is still 1. When we go up, since there are no more child nodes to visit for this parent node, we make the tentative value 1 for this node final. So this becomes now the final evaluation value for this node. So it's 1. And when we go up back to this parent node, we update the tentative value of that node, which is 5, by getting the maximum between 5, the tentative value, and the final value of the recently visited child, which is having a final evaluation value of 1. So the maximum is still 5. When we go up, we make this tentative value 5 for this node final. Okay? This is now a final value. And when we reach back to the root node, we update the tentative value of the root node 3 by getting the mean of 3 and 5, the final value of the recently visited child node. And of course, the minimum value is 3. So we are done with the depth first search traversal and backtracking, and we make this tentative value of the root node, which is 3, to be a final value since there are no more child node of the root node to visit. So the final values now of the interior nodes and the root are, for this interior node it is 3, for this one it's 1, for this is 3, for this it's 2, for this one is 5, for this is 5, for this one is 1, and for the root node it is 3. Now, remember that the process we are doing here is backtracking, which involves applying these two rules, rule number 1 and rule number 2. And remember that in backtracking, we are not applying rule number 3 yet, and so we are not skipping or pruning some of the nodes. This requires that we are going to visit all of the nodes of the tree. And that's why we are assured that we will get the optimal or the best solution that we are looking for. But the disadvantage is that it would take us longer time to finish the process since we are required to visit all of the nodes in the tree.